Dr. Ranjit. Good morning, Dr. Ranjit.
Good morning, sir.
Here. Dr. Ranjit.
Hello. Hello.
Good morning, Dr. Ranjit.
Good morning, sir. Am I audible?
Good morning.
Good morning, sir. Am I audible?
Hello, sir.
Hello, sir. Am I audible? Hello.
Yes, you are audible, sir. You are audible.
Okay, sir.
Okay, you can share your screen, Dr. Ranjit. You can share your
Yes.
screen. I have made
Yes.
you the presenter.
Okay, fine. Okay, sir.
Dr. Ranjit, we will start within 5 minutes.
Okay, fine. Okay, sir.
Good morning to all of you. So, we are going to start this session, and it's a great pleasure to me to introduce our session. This session is speaker, Dr. Ranjit Ravindranathan Nair, who will deliver a talk on multi-robotic systems, consensus, and coordination. Dr. Ranjit Ravindranathan Nair is presently Assistant Professor, Department of Electronics and Communication Engineering, IIIT Pune. Dr. Ranjit Nair received his PhD in Control and Automation from the Department of Electrical Engineering, IIT Kanpur in 2017. After this, he was working as postdoctoral fellow in Intelligent Systems and Control Lab at IIT Kanpur. As a part of the PhD program, now Dr. Nair was involved in research projects sponsored by ISRO and Department of Electronics and Information Technology, Government of India. Prior to joining for the PhD program, he was working with L&T Infotech Limited, Chennai. Currently, he is, as I have told you, is working as assistant professor in the Department of Electronics and Communication Engineering, IIIT Pune. Dr. Nair has many publications to his credit in IEEE journals and Tier 1 IEEE international conferences in control sciences. He has co-authored a book with Professor Lakshmi Dhar Behra from IIT Kanpur on intelligent control of robotic systems by Taylor and Francis Publications, RC Press. Dr. Nair has also received Best Paper Award in ACODS 2012 International Conference held at IISc Bangalore in February 2012. He is the reviewer of many IEEE transactions, including IEEE transaction on industrial electronics, IEEE transaction on industrial informatics, IEEE transaction on cybernetics, IEEE transactions systems journal, and IET electric power application. His primary research interests include multi-robotic systems, cyber physical systems, non-linear control systems, and multi-agent systems and intelligent control. So I would request Dr. Ranjit to please deliver his invited talk. Dr. Ranjit.
Yes, thank you, sir. Am I audible, sir? Hello?
Yes, you are audible, sir.
Yeah. So good morning, all of you. So, so today the session I'm going to take is on multi-robotic systems. So multi-robotic system is one of the key research domain in the field of robotics. So when we talk about this multi-robotic system, I think we should, especially past 1 decade, there are lots of researches happened in this field. So when you talk about multi-robotic system, I think we should start from the multi-agent systems. So this is a very common scene in the nature, basically. I hope you have seen this. So multi-agent biological systems. This concept of multi-robotic system or multi-agent system has been derived from the biological systems. So this you have seen the flock of birds, this school of fish or herd of animals. This is very common in nature. You can see this common scenes. So this I told you this concept has been derived from these biological systems. So a research first of its kind in the biological systems was conducted by a biologist, Steve Vogel. So he just implanted some heart monitors in white pelicans to find aerodynamic benefits behind the flocking of birds, or the benefits, energy benefits, or benefits regarding the behind the flocking of these birds. Basically, you can see the migratory birds will fly for kilometers. Even they may cross the continents. So basically, a huge amount of energy is needed. That to actually small living being is doing this. So of course, it is a major. This is one of the attraction or motivation for the researchers to look into this field and to mimic this technique and to extend this technique to the artificial systems. Okay, so when Steve Vogel has conducted this experiment, and he has found that there are some energy benefits for these birds when they are moving in this V-shaped formation. So this is very common, and you can see that we are inverted V-shaped formation of birds is very common. So when he found that there are some aero benefits for the trailing birds in the two lobes of V, so especially these birds are not flying, they are not in the same plane when they are oriented in V shape, so one above the other, so that the aerodynamic drag is little less for that. So that is the observation out of his study. So this, so that is one of the observation out of this study. And second thing is, one of the most interesting observation out of this study was that this individual decisions taken through the local interactions by these member in the formation is coming out as the global behavior, basically through local interaction. So the individual decisions taken by each agent, but through very local interactions only, but it's finally coming out as a global behavior. So they are actually, there is no one-to-one communication between all the agents here. So the agents are, the members are interacting with the immediate neighbors only. But finally, it is coming out as a global behavior, and there should not be any collision, and they are actually following the path. There is no obstacle avoidance. There is obstacle avoidance. There is path following. Everything is there, but only through local interactions. And apart from that, I told you of the aerodynamic benefits also behind the walking of birds. Was induced drag is less due to the aero interactions, and because of this, vortices are distracted. There are some aerodynamic reasons, like downwash region. This trailing birds are being placed. There are downwash region of the leading bird, where the trailing bird has been placed, so that this induced drag is less to the aero interactions. So anyway, that is the benefit for birds. So there are some swarming behaviors. So these are the common swarming behaviors which we observe in biological systems: flock joining, path following, collision avoidance, obstacle avoidance, reconfiguration. So these are some of the common behaviors we observe in biological systems. So this scientists has explored this concept and try to extend this concept to the extend this one to artificial systems. And this has paved the way for the emergence of this area called multi-agent systems. So this very broad area. So it has lots of applications ranging from power systems and microgrids to the robotic systems to space systems, and in fact in business models it has been used. So this very broad concept, but in our case we are actually our agents are robots. So we are trying to use this concept for the formation of multiple robotic platforms. So here these are the common swarming behaviors. Flock joining. Flock joining means making the flock. Path following means, of course, they have to follow a path to reach the target or something. Collision avoidance means avoiding the collision between the agents in the formation. Obstacle avoidance means avoiding the obstacle, external obstacles when they're moving in a cluttered environment. Of course, reconfiguration is also possible. If you have observed the birds in nature, you can see that when you're making a formation, especially V-shaped formation, the tip of V is a leader position, and the two lobes of V have trailing birds. And again, this birds at tip is been changed sometimes. Okay, after some time, leader position has been interchanged with the trailing birds, because the leader energy efficiency is less. Leader needs, actually it's not free flying experience, but trailing birds has free flying experience. So free flying that benefits are there. So that actually they will reconfigure in between. So this reconfiguration can be, these are some of the swarming behaviors which we are trying to mimic in the robotic systems also. So collective intelligence is one of the major advantage of the multi-agent systems. So we are actually delegating this cognitive aspects to different agents in the system. So this concept is also been used in many applications. And cooperative control. So of course, so our case, actually we are looking into multi-robotic systems. So when you talk about multi-robotic systems, I told you, so it's one of the key research domain, especially lots of researches has happened in this area for the last 1 decade. So the first question which comes to our mind is why we need multi-robotic systems, why we need multiple robots to perform. So I think better we can explain using some of the pictures which show here. There's a few examples which I can show, demonstrate to this one, to point out this the relevance of the robotic formation. Some other applications. So one is like then cooperative transportation, then risk and surveillance and risk operations and search. There are numerous applications are there. So we are coming to that. So of course, certain type of applications, like there are some limitations for a single robot to handle. So especially for a cooperative transportation, you can see at the right-hand side, it's carrying a heavy object. So of course, it's quite difficult for a single platform to carry it, and it can be better manipulated by multiple robots, just like the human. human labor. So you can think of the same way. It's quite difficult to, because the payload capacity is more, in that case, it's quite difficult for a single robot to handle that. So we can employ multiple robots. And of course, the figure you can see below, the first two is for the search or risk operation. In the case of fire, outbreak, so this is basically a risk operation done by the quadcopters. Okay, four quadcopters, aerial robots performing the risk operation in the case of a fire outbreak. So there are many applications. I'm going to show that. So, but the major applications for multi-robotic system is in about this. If you're categorizing the military applications and civilian applications, so military, there are many other in military applications like surveillance applications, search applications, risk and security applications. Already these robots are being employed, these military applications. So there are lots of advantages. I told you it is very adaptable. The accuracy is more. The work precision is more. Energy efficiency can be improved. Of course, it's very much adaptable. Even if multiple robots are there, if one of the platform got fail, any failure happens to one of the platform, the mission will not completely fail. So because the rest of the members can continue the task and complete the mission. So that is there. And again, the flexibility is also more, and again, quality of the work also can be improved if you are deploying multiple robots, especially for certain types of applications. So it's not like every application needs multi-robotic platforms, but there are certain applications multi-robot systems can perform better than a single platform. So civilian applications, of course, there are many are there. So one of the work is power line and patrol, pipeline and power line patrol. This is basically the work which I've done with my postdoc. So this is like multiple robotic systems are used for pipeline, oil and gas pipeline patrolling, night patrolling, and detecting the faults. Usually the oil and gas pipelines usually run through desert lands. It's coming from Gulf countries and all, right? Oil gas pipelines. So it may be going through kilometers through the passing to the desert lands. It's quite difficult for a human being to go and inspect the faults of any gas, any leakage or something, oil or gas leakage. So in that case, multi-robotic platforms have been deployed, aerial robots, as well as aerial robots are better, but basically aerial robots have some limitation for the battery capacity. So we cannot actually fly these robots for a long time. So in that case, actually, we need a Land Rover also to follow that. So that as a base charging station, we can keep a mobile robotic platform also along with this formation. So it's basically a multi-agent system with aerial robot, a mix of aerial robot and Land Rovers. So power line patrolling. Power lines are generating stations are usually at remote locations. So of course, the power line fault can happen due to some natural disaster or some climatic variations. In that case, it's quite difficult for a human being, or in the manual inspection, it's quite difficult. So we can think of robotic systems to, especially multi-robotic systems to do this patrolling. Rather, a single platform, it's quite difficult. It's time consuming, and of course, there's a limitation in the area of coverage for a single platform within a time span. Is it from the time and quality? If you want to improve, of course, we can deploy multiple agent system, multi-robotic systems for this power line patrolling, especially in the night time. And then farm aerial spraying. This already many projects has happened in MNNIT control also. Farm aerial spraying and disease detection. So big farmlands of kilometers, big farmlands, is quite difficult to go and inspect the disease and the individual plants. Okay, so it's quite, so we can deploy multi-robotic systems, multiple aerial robots to go have inspection, and also pesticide spraying also we can deploy this aerial robots. And forest fire suppression, cooperative transportation, this all I explained it. So all these cases we can think these are some of the civilian applications which we can use multi-robotic systems. So in fact, multi-robotic systems will perform better in this particular applications. Next is like search and risk operation. I already explained. These are like aerial robots, the surveillance applications using this Land Rovers. Then of course I told you this multi-robotic systems, this multi-robot system concept has been extended for satellite systems also. They are also sort of robots, autonomous systems. So this is basically we already been used. The concept of multi-agent system is already been used in space systems, multi-spacecraft systems. There are certain applications where we need multi-spacecraft systems. Localization, we can use multi-agent systems. We can deploy aerial robots. So there are these all applications I told you. Search and risk operations. Of course, the area of coverage is limited for a single platform. Those cases we can go for multiple platforms to extend for higher resolution data extraction and all. So So I told you satellite formation is one of the already this type of missions are being deployed by various space agencies. So including, I mean, recently there was a similar mission by NASA. So the space formation, there are many applications. One of the application is like interferometry. Interferometry means light interference patterns are being used for the interplanetary studies. So interferometers has to be placed at different platforms. So in that case, the different multiple aerial platforms are needed, space platforms are needed. So where interferometers to be placed. So for that, actually, we may need multi-satellite system and end-to-end docking operation for International Space Station maintenance and all. We have to, we may need multiple spacecraft. For rendo means chasing of one spacecraft another, and docking means get it mechanically coupled. So render and docking operation is also very common application. It's been used in space systems. So this is very common. And again, spacecraft formation is another one of the biggest advantages, like for higher resolution data extraction, especially for space systems which is in the low Earth orbit. So the area of coverage is limited. So in that case, we can go for multiple platforms, and the sensors can be multiple sensors from multiple platforms can improve the resolution of the data. Okay, so that is also one thing. And launch cost can also be reduced in that case. Instead of a single bulky platform, we can think of deploying multiple small micro or mini, even nano satellites are also nowadays being used. So micro satellites or nano satellites, small satellites instead of a single bulky platform. There are many advantages. Okay, certain type of applications, this formations will work better than a single platform. And coming to that, so these are many applications are there. So a few I have just shown you. You can also explore this applications of this multi-robotic system. So then now we are coming to the basic modules in a multi-robotic system. It's not only for, these are the basic modules, but it's not for multi-robotic system. For a single robotic system also, these are the major modules: perception, cognition, and actuation. So, but I just want to just pass out this. So the perception module means, of course, the sensing part. The sensing part will comes in the perception module. And then next is the cognition module. The cognition module, that's very integral. This is the most important module, can say the cognition module. So the path planning, control, computation, communication, all the things are integrated into cognition module. That's very important. And the actuation module, all are equally important, but lots of research scope, basically people are mostly looking at cognition part. And actuations also, there are, of course, we need to actuate the physical processes. We need actuators, electric motors, or what are the pneumatic or hydraulic. There are advanced actuations are also possible nowadays, like smart polymers. And new actuators are coming out. Smart actuators are also coming. Perception also, there are, is very huge, is a very broad area, perception module also. Like the perception means sensing. Nowadays, mostly the commonly used sensor is camera nowadays. So computer vision has lots of scope. And again, that all comes in the perception part. So our part, we are mainly concentrated in the cognition part. Because what makes a robot more smart is intelligence. So hardware configuration may be the same for multiple robots, but what makes the robot more smart is basically the cognitive module. So among the cognitive part, the control is very important. Path planning and control, especially for the robot navigation perspective, of course, control and path planning is very important. So when you talk about multi-robotic systems, so the multiple robots are there. Of course, they're communicating through a local network or any cyberspace. So in that case, the communication things also will come into picture. So in that case, actually, a cognitive module has to take care of the communication aspects as well. And of course, a multi-robotic system is a very complex system. So computation complexity also matters a lot in that case. So that's why cyber physical robotics, a multi-robotic system, all the things will take care of the computational as well as the communication aspects, the multi-robotic systems. So it's a very broad area. So, but major thing is planning and control. That's very important. But apart from that, these all things will, communication part is also important on a single robotic platform also, but multi-robotic platform is very important because when we have to get these robots connected. So we'll see the details to that. So these are some of the objectives in multi-robotic system, very common objectives in multi-robotic formation applications. So like if you have multiple robots, not necessarily all the objectives are there, but very few I just quoted here. So for formation maintenance, if we have a multiple system having multiple robotic platforms, of course, formation maintenance is one of the we need to maintain the formation throughout the mission. So that's one of the objectives. Then formation reconfiguration. Sometimes the formation cannot actually be, they need to reconfigure at some cases depending upon the environmental conditions or depending on the application. Sometimes they may need a reconfiguration might be needed. So trajectory following, of course, they have to follow the desired trajectory, because there's a desired trajectory we need to define for the velocity or the path, the position or velocity or the acceleration or whatever be. Then we need trajectory following. Obstacle avoidance, of course, if it is working in a very cluttered environment, it has to take care of the obstacles in the environment. And next thing is like the fault detection, resilience. So resilience to the actuator sensor fault and the network faults. So the actuator faults can happen for that. That's very critical. If the actuator is faulty, then actually nothing will happen. So we have to only option is like we have to isolate that particular robot in the formation. But the mission cannot be affected. That's advantage. If I told you, that's advantage of multi-robotic system. Even if one of the robot goes faulty, rest of the formation can reconfigure and maintain and can continue the mission. Sensor fault is also very critical. So of course, the fault happens to sensors. So that is to be detected on time, and also if it is very critical, in that case you have to isolate. Otherwise, if it is like tolerable, so of course then we can go for a fault tolerant algorithms are available. With the partial faults, then we can continue the mission. Actually, we don't need to isolate a member if some was a partial fault or a minor fault is happening to one of the robots or one of the agent. So this there are fault tolerant algorithms, robust algorithms are available to deal with such type of fault. So we are actually, I'm going to show one of the case study based on the fault tolerance. And second thing is communication consensus based formation. Communication consensus means, of course, I told you when you have multiple robotic systems, multi-robot systems. So here, communication aspects also you have to consider, because robots are communicating sometimes through cyberspace and sometimes through a local network dedicated for this particular formation. So in that case, we need to take out the communication aspects, because we should communication complexity should not increase. Is it? So I told you in the case of birds, you have seen that the birds are not all the birds are not interacting with each other. They are actually communicating with respect to the immediate neighbor. Finally, it is coming out as a global behavior. You can see that the shape is maintained, but even there are flocks of thousands of birds are also there. That such type of flocks are also there. In that case, you can see there's no collision avoidance. But actually, they are not interacting to all the agents, but still they are actually all satisfying all the objectives through local interactions. So communication network is very important actually. So we can actually think of a graph-based communication, the communication protocol for this multi-robotic system. So that case actually, that is basically comes in communication consensus, an agreement between these agents and the formation regarding the communication aspects. And next is network resilience. So when this network, when the agents are networked, there are many faults, uncertainties in the network, like packet loss, then delay. These all things are some of the network uncertainties in the system. So of course, when we are talking about a formation control algorithm, so it has to be network resilient to the network fault. So I told you the major network faults, packet loss. Packet can be lost at a certain instance. Basically, we need to get the sense data at every sampling instance. Okay, data sent from one node should be received at the other receiving end at every sampling instant at the desired time. So sometimes actual data has been lost at some instance, and sometimes it's delayed. So all these cases, the system performance will be affected. So this is all, but of course, we can think of robust defined algorithms to deal with this type of uncertainties. So that is network resilient algorithms we can think of for the formation control. So this is basically comes in network resilience. So this consensus based formation also, there's one case study I'm going to show, the real-time experimentation which we have done. So these are the basic modules. I hope you all know this. So if you have those who work in the field of robotics, so these are the basic modules in a multi-robotic system. Okay, it's a control module, I'm telling you. In the control module, these are the basic blocks, you can say that, or can say cognitive module. That's precisely cognitive module. So here, see this control, the basic modules are guidance, control, navigation, and of course the communication modules. Okay, computation aspects will come in everything. Nowadays, even computation capabilities for sensors also nowadays, because sensors are very smart. coming out. New sensors are very smart sensors, so they are having computation and communication capability also. Okay, and again, actuators are also smart. Actuators are also nowadays available, and so all how computation aspects will comes in every module actually. So now, when you come to the control module, the control is very important. We need to control the behavior of a system. So of course, in the case of a mobile robot, so we need to control the basically velocity or the force. Can say this apply to the motors to control the to make the robot follow the path, okay, desired path, the velocity trajectory or the position trajectory. So we may have it. So we need to plan the path first for the robot navigations, and our control module will take care of that to make this robot to follow that desired path has been developed. So guidance module is basically developing the desired path. Okay, so based upon this all the sense data and based upon the present output and the data sends from the neighboring agents and all. So guidance module will decide the desired path for each agent. So the path planning is being done by the guidance module, basic guidance. So navigation module means sensing part is called navigation module. Navigation means actually finding the position or orientation of an object. That's basically navigation. So navigation module take care of the sensing part, guidance part will take care of the path planning, and control module based upon sense data and the planned path. The control module will make the robot to follow that path which has been planned by the guidance module. So the control commands has been given to the ith member. So this is basically a block schematic for one of the member, ith member. So each member has supposed to have it's a decentralized module actually. It's not a centralized control I'm not talking about. Basically completely decentralized control. Okay, each robot is supposed to have onboard computers and all the onboard systems to sense the data, and again processing power it's having onboard. So it's not like actually an off-board system is controlling all the agents. It's also possible centralized way. Some type of indoor applications we can use it, but mostly decentralized way we are controlling. But each agent has its own basically all these things. I mean the computation element. So the next is the ith member is communicating to the jth member, of course, the communication module. So these are basically this called GNCC loop, guidance, navigation, control, and communication loop for the ith agent actually for one of the member. So we are basically concentrating in this guidance and control part, and that's very important in this case. So coming to the formation architectures, so there are different types of formation architectures are available. So quickly we'll go to that. Then leader follower based approach, behavior approach, and we are leader based approach. These are the basic three architectures, formation architectures. So leader follower based approach is very common. You have seen the case of birds. So one of the agent in the formation is assigned as the leader, and the rest of the agents will follow the leader with respect to follow the leader with an offset. So that is basically leader follower based approach. So once they are in formation, the followers will follow the actual dynamics of the leader once they are in formation. So behavior based approach means all the agents, there is no leader or follower such type of categorization, but these agents as a whole will try to mimic the swarming behaviors. All this flock joining, path following, collision avoidance, obstacle avoidance. That's why it is called behavior-based approach. So next is virtual leader-based approach. So virtual leader-based approach means, and again behavior-based approach, the control input. So if you have swarming behaviors, multiple swarming behaviors, like flock joining, path following, obstacle avoidance, and multiple objectives are there. Net control input is basically the weighted average of the control input due to the each swarming behaviors. So that is the importance of behavior-based approach. So that not necessarily the case of leader follower-based approach. Okay. So we have multiple swarming behaviors. Sometimes the formation as a whole has to avoid obstacles, and sometimes it has to reach the goal-seeking objective it is having. Sometimes it has an objective to avoid a collision with respect to neighbors. So the multiple objectives are there. So there are multiple objectives. So the net control input is basically the weighted average of all this, the control inputs to the individual swarming behaviors. So that is basically behavior-based approach is all about. Next is virtual leader-based approach. So virtual leader-based approach means it's nothing but there is no physical leader there, but there is a virtual leader. That means a formation as a whole as a rigid structure. So and again, one point in that rigid structure is designed as a virtual leader, basically a point in that structure. So it is like not flexible. So and again, the trajectory of each member in that formation is defined with respect to that point. That's called virtual leader based approach. So these are the three major formation architectures been used in multi-robotic systems. When we are coming to research aspects, a few things I just want to point out, because when you are designing a multi-robotic system, the major challenges when you are dealing with the system is, of course, resource optimality. So because we may need more resources, is it, in the terms of communication sensing. So the resource optimality is very important when you are just going to design a multi-robotic system. Okay, so the communication requirements is one of the major, so it was a major thing, and we need to optimize resource requirements in terms of communication requirements and also sensing requirements. Okay, so next is like of course we have multiple robots are there and it's very complex, so modeling is quite difficult, system modeling is quite difficult, and again system should be able to adapt to the operating conditions like environmental conditions and all the things. If it's cluttered environment, so we can expect any sort of uncertainties in the environment, so it should be adaptable to all these changing environmental conditions, and it should be the performance, the speed, it should be fast enough to perform all the complex maneuvers. So otherwise we cannot deploy multiple robotic systems because, okay. So next is the resilience. I told you this fault tolerance to actuator faults, sensor faults, network faults, delay and packet losses, the sensor actuator, all these things should has to be taken care actually if you have multi. That's actually true in the case of single robot system also. Multi robot system also very important, but network resilience is more critical in the case of multi robotic system. Other faults like actuator and sensor faults are even equally important for single robotic platforms also. Next is dynamic weight allocation for different swarming behaviors on runtime. I told you when there are multiple robots are deployed, there are multiple swarming behaviors. It's like sometimes the robots has to maintain a formation. Of course, it has to reach a goal point. It has to avoid obstacle. It should avoid collision with the neighbors. The multiple objectives are there. But all the time, we cannot give equal weightage for all these behaviors. Sometimes obstacle avoidance is more critical. Suppose it is very close to an obstacle and it is very, in that case actually obstacle avoidance should be given more weightage at that case, is it? So sometimes actually then there is no obstacle, of course it has to be weightage has to be given to sometimes the collision avoidance. So the weight allocation to different swarming behaviors is varying basically, so depends upon the operating condition. So we have to dynamically allocate the weights for the different swarming behaviors, all these path following, flock joining, or whatever be the swarming behaviors. That weight allocation is basically a problem, dynamic weight allocation for the different swarming behaviors. And again, when I'm just coming to control aspect, so here in this talk, I'm just going to show especially major 2-3 case studies. So these real-time experimentations we have done. There are many approaches are there. For the multi-robotic systems. So then, as an example, I'm going to show three works, the real-time works which we have done, and also some of the experiment demonstrations also I have to show that. So for that. So let me just go to a little bit about the control part, because the major formation control approaches. I'm not going to detail about this far. If anybody wants to know more, of course, I'm happy to explain. So basically, formation control, I told you there are many approaches. So major, we can classify the formation control into two broad categories. One is called time triggered controls, and second is event triggered approaches. I'm just categorizing in that way. So time triggered means we are triggering the control at every sampling instance. Okay. We are giving the control commands to the robot at every sampling instance in time triggered approaches. And when it comes to event triggered approaches, the control is not triggered at every sampling instance because that's not needed actually. That's a 4th generation control, event triggered approaches. So in that case, control is triggered only when it is required, or when an event occurs. Event is basically decided using theoretical analysis. We can define the event. So control is triggered only whenever it is needed. So nowadays this is very actually you can see lots of researches are happening in this field of event triggered control. Even sensing is also event triggered nowadays. Many systems sensing means the sensor will sense the data, but it is not sending the data at every sampling instance. Whenever it is needed, whenever the data is whenever the control update is needed, then the sensor will decide whether it is to be sent to that base station or not. Then only sense data has been sent. So there is a self-triggered approach. Event triggered approach usually means control is updated only whenever it is needed. Otherwise, actually the previous instant control trigger is enough. So that actually we can reduce the communication requirements in that case if you are going for event triggered approach. Okay, if you don't have to communicate, the control need not communicate with the system every time. Whenever it is required. then only that which instant is required, that is decided by the event. That's basically an event design is there. So we have to design the event. So we have to find the event condition. Based upon that, we can decide which instant this control is to be updated, control command is to be triggered and all. So that will come to that. So time triggered approach, I told you, we are giving the control commands at every sampling instance. So many approaches are available: feedback, linearization, backstepping, optimal control, sliding mode controls. These are some of the major approaches which we are using. Information control. So feedback linearization is basically like the nonlinear technique. Linearizing through feedback, backstepping, recursive approach. Optimal controls are also there. Optimal controls means this is a linear quadratic regulator. The control is such a way that it optimizes an energy objective function. Model predictive control is a planned control, but optimal control itself. Sliding mode is one of the most robust control. Nonlinear control is basically a variable structure control. The control has varying structures depending upon the operating condition. So this one of the approach, I will show a little bit details about one of the approach, just to give an introduction to that. So among this, and next is fault tolerant controls. So I told you about the fault tolerance, like actuator, sensor faults, network faults. So this all type of faults are happening in the system. But among the fault itself, we can categorize into two types. What are the fault? Minor fault and a major fault. So the thing is, when you just categorize the faults into minor and major faults, the major faults, of course, sometimes we have to completely isolate the robot, because robot cannot work well in the formation, cannot perform well in the formation. So only option is to isolate that particular agent in that case. But in the case of minor faults, we can think of a fault tolerant formation algorithm. So that is basically the two things. So we are going to deal with both these things, minor as well as major faults. The one of the case study which I'm going to show is based on that. So how to deal with both this major and minor faults. One of the approach which we have used to deal with minor faults and major faults in the robot formation. So just quickly, I will show what is the model which I have used and what is the basic path planning technique, the basics of the path planning technique and very basics of the control also. Quickly, I will show that with 2-3 slides. Then I will go to the case studies. So this is the model which I have used, the mathematical model. I didn't go for any heuristic models because the robot is a very simple mobile robot. So it's basically Pioneer robot we have used for the experimentations. So we have used a kinematic model. It's a 2-wheel differential drive robot with almost 17 kg weight and having its 2-wheel differential drive. So there are 2 wheels are there. So these 2 wheels are separately controlled. Differential drive robot means we are driving this individual motors separately. So this has 2 wheels and there's a dummy wheel for the mechanical support for this particular robot. Yes, I hope I'm audible. So if any
Yes, sir. You are audible, sir. Dr. Ranjit, you are audible.
Yes, sir. Thank you. So this case, actually, we have defined this the kinematic model with the center of gravity of this robot first. Then actually, with respect to center of gravity, if we are defining, it's basically x is going to be cos theta, x dot will be cos theta, y dot is going to be sin theta, like that. We can make it. The v is the velocity component, velocity along this longitudinal axis. Then in that case, we can say v cos theta is basically x component of velocity, v sin theta is y component of velocity, like that. That's the basic model which people used it also, but there's some disadvantage for that model. So because we cannot decouple the control inputs out of that, it's quite coupled model. So we are going to a little bit modification for the model. So the model used is we are actually redefining this model with respect to a point A at a distance of L meters from the center of gravity of the robot. So this way we have redefined this model. So we have derived this model. So this is all available in literatures, this particular model. This is basically unicycle model. So it's called unicycle model because when we're designing this particular model, we are assuming that there's only a single velocity parameter and there's only a single angle parameter. So unicycle, that's the difference between unicycle and bicycle. Bicycle model means basically 2 velocities will come. Both the wheel velocities will come into picture in the dynamics. But unicycle model means we are considering it as a system with 1 wheel. So there's only 1 velocity has to be considered in the modeling. So in this case, you can see in the model, V is the velocity of the bot and omega is the angular velocity. V is the linear velocity, omega is the angular velocity, theta is the heading angle. L is the distance with respect to the center of gravity. X dot and y dot are the velocity components along the x and y directions. And our aim is just to control this x and y and y, the position x and y of the board, by controlling the velocities, the linear and angular velocity of the boards. Of course, we have to control that that the velocities, the inputs to the motors. The low-level control perspective we're talking about, we need to do the voltage control. But high-level control perspective, we can use this model to design the controllers. So we need to give the control commands for the velocities, linear and angular velocities. So here, this is the kinematic model, but we can go for a dynamic model also. Dynamic model means we need to differentiate these two equations once again. So in that case, force and torque will comes in this equation. So in that case, force and torque are the control inputs. So here, but in this case, the control inputs are the velocities. So by controlling these velocities, we are controlling the positions. So controlled parameter is positions, and control parameters are the velocities, linear and angular velocities. So this, when you're coming to that, so this is the model which you used. This model is enough, because when you have to go for a very like a very complex board with mass is greater than this, mass is greater than 50 kg or 100 kg. So in that case, more than 100 kg especially. So in that case, actually, of course, we have to think of a high fidelity model, including the second order model, where a force and torques will comes into picture, because inertia and all the mass, everything will have some effect in the dynamics. So in that case, we have to go for a second order model. If you have even if more complex system like a aerial robot or something, we can think of a third order model also. Like actually the acceleration, this is basically velocity equations. In second order model, basically it comes the acceleration. Third order model means the jerk dynamics will come. So fourth order models are also there, snap dynamics. So x for double dot, for x is it x for dot. So this is so you can think of if a system is very complex, you can go for fourth order model, or whatever be that. So here actually for this robot is very simple bot. So mass is also not much high. So this kinematic model will work well. Path planning techniques, there are many path planning techniques are there. So out of this, these are the major things, major two approaches I'm just going to point out. There are many path planning techniques are available. Especially nowadays, there are many heuristic approaches are available. Neural network based approaches for C, all the heuristic algorithms are heuristic approaches are available for planning the path of a robot. Okay, so even optimal control approaches are there to plan the path based upon the operating conditions. So, but major classical approaches which we use for planning the path of a robot is geometric approach, and basic next is artificial potential based path planning. Just to introduce two things, there are many things out there you can explore if you're interested in this. So this just one example I'm going to do the path planning techniques, and one control technique also as an example I'm just going to show. So here in this case, geometric approach means based on the formation geometry, we are redefining the dynamics, and we are controlling that separation as well as the angle. Okay, geometric approach. Second is artificial potential based approach, whereas a mathematical function. Artificial potential is a mathematical function, which is a function of the distance parameters, distance between the robots and the formation and all. So based on this mathematical function, basically we are making the velocity of the agent to follow the gradient of that particular mathematical function. So I'm coming to that. Sometimes this mathematical function can be function of only the physical parameters. That means the distances or velocities only. Sometimes cyber parameters like network parameters, this network routing probability, all the things can also come in that mathematical formulation. Okay, so that is in cyber physical robotic systems. We will go for that formulations. So anyway, for geometric approach, I told you the basic purely based on geometry of this formation, we are defining the dynamics, and we are looking for a control framework. So this is a simple case of a two robot formation, having one robot here, the leader one, and here is the follower robot. So the robot, of course, the follower has to follow the leader with a particular offset. At the same time, a particular heading angle also to be maintained. So heading angle. Heading angle means the angle between this this Lij vector and this this one velocity vector. So this is also, these two objectives are there. So both these things we are controlling. The distance between these robots as well as this heading angle we need to control. So of course we need to redefine the dynamics in terms of that. That is basically dynamics here. So mathematically we can formulate Zij means Lij and Psi. Lij means the distance vector, this radial distance between these two members, and the Psi means the heading angle. Okay, heading angle. So these two things we are controlling. So this controlled parameters are L and Psi, and the control parameters are U. So U is basically the force, this velocities, linear and angular velocity. We are just redefining the mathematical model, and we can going for a control framework. Okay, so but there are many nowadays many complex robots. It's quite difficult to mathematically model this system. So in that case, data-driven models are also available, and people are using that data-driven models based on this heuristic approaches like neural network approach, or even deep learning models are also available. So many depends upon that. For simple robotic systems, it's fine. Good mathematical models are there. It will work well. So when it comes to the next path planning models, just quickly I will go through this artificial potential based path planning scheme. So in this scheme, I told you this the path is decided by a potential function, mathematical function. Okay, so here we are actually making Zi means the velocity of the ith robot, Zi dot, Zl dot means velocity of the leader. So Zi dot minus Zl dot. That means relative velocity between the agents. So that is supposed to follow the negative of a gradient of a potential energy function. Okay, so this potential energy function we need to define in terms of the distance separation between the agents. So that is basically that we have to formulate. There are many versions are there for defining this J. J means a potential function, gradient of this potential function. So we have to take the gradient because the position is basically a vector. So of course we are taking the derivative as a gradient. So negative of the gradient of this potential energy the velocity has to follow the negative of the gradient of the potential energy. So this usually when the multi-robotic system, when this robots are making a particular formation, this mathematical function has two parts. So one part is called attractive part, second part is called repulsive part. So attractive parts for predominates if actually the agents are at long distances. So that it has to come, it is very far apart, it has to come to a formation. So the attraction will prevail, and so the agents will be attracted towards each other. In that way, the mathematical equation has been formulated. And when these agents are very close, it should not collide, right? So that when the distance is very small between the agents, the mathematical function is such a way that the repulsive part of the mathematical formulation will predominate, so that the agents will repel away. Okay, and when the attraction will balance the repulsion, when the robots are the desert formation. That means the net attraction is equal and opposite to repulsion when actually the robots are in formation. So that way the parameters inside the mathematical function has been tuned. For a particular distance, there are many ways. So one method is like we can tune it for a particular distance value, some 1 meter or something, or whatever, for example. So based on that, we can tune the parameters of the mathematical function to make this formation. So at that particular 1 meter distance separation, attraction part is equal and opposite to the repulsive part. So the net potential becomes equal to 0. So now there is one way. Second way, I told you this mathematical function can be defined in terms of the cyber parameters, like this routing probability, the link reliability. This all communication parameters can be included in designing the this one potential function. So this purpose, if you want to know more about this artificial potential function with path planning, you can refer this paper which is shown here. So this there are many methods are available. This one of the method I told you. This is not only for mobile robots. APF method, artificial potential field-based method, has been used for manipulators also. Now I told you some examples I'm going to show. Google for the different objectives based on objectives. So goal-oriented motion, that's one of that objective. The robots has to make a formation and has to reach the goal point. Is it? So if you know the goal point, so of course we can think of a simple potential function to reach the goal point. This is a single robot case also. You can apply this technique. It's not only for multiple robots, because goal seeking is there in multi-single robot system also. Here this is the potential function for goal seeking, where x represents the actual position of the robot, x goal represents the position of the goal point. So simply a mathematical function, gamma is a scaling factor. So just to avoid velocity jump, so we can fine-tune this gamma, so that is to control the velocity. Otherwise actually the velocity is supposed to follow the gradient of this particular potential function, negative of the gradient of this. So when x becomes equal to x goal, so this is equal to 0. Okay. So our aim is to make x to reach x goal. X is the actual position of the robot. X goal is the goal point. So we are driving the robot to reach the goal point. Second one is called, I told you about attraction repulsion. This is basically attractive part is proportional to the distance separation. Y is the distance separation, is a constant. B, C are also constants. Y is the distance separation between the agents basically. So in that case, this attractive part, that means it is proportional to the distance separation. As the distance separation is very high, this part will predominate. And this, when the attraction, this is a repulsive part, that means if it is distance is very small, this part will predominate. So this is basically some of the examples. There are potential functions for obstacle avoidance also. I didn't show here. That's also very simple. 1 by the distance separation, the whole square, minus 1 by the safe distance whole square. So simply a potential function for obstacle avoidance that's available in literature. Okay, so if you have the, based on the distance with respect to the obstacle, so we can actually think of making a mathematical function which will, so as to make the robot repel away when it comes closer to the this obstacle. So when it robot comes near an obstacle, it should repel. Okay, for goal part, that it's an attractive type of potential function. So this is basically all about. Then now we got to the controller part. So of course we need a controller to make these robots to follow that path we designed, right? So we got a desired path for the position and velocity. So we got this velocity especially. We are making this. This is basically desired path for the relative velocity. The negative of the gradient of the potential is the desired relative velocity path. Relative velocity trajectory. So we got it. So if you integrate it, you will get the relative position trajectory. So now we got the desired path. So now the next task is to design a controller to make this robot to follow the path. Okay. And again, of course, disturbance, subjection, everything. If you are just commanding based on a open loop way, so basically it may not work well if the disturbances are happening in the system. So of course, we need a controller. So for this, all these reasons. So one of the control, I'm just quickly showing this sliding mode control. So this is this control technique we actually used in this case studies which I'm going to show, but not conventional one. It is improvised. The conventional sliding mode technique, I will tell you what is this control technique. There are many techniques are there, and there are lots of good techniques are also available, but it's one of the commonly used technique, and lots of research has happened in this area. So this is a sliding mode control. There is a variable structure control. It is a variable structure control. For explaining this, so I'm just considering a small system dynamics given by x dot equal to f of x ut, where x is the system state parameter to be controlled, u is the control input, and t is the time period. It is the time. So this is the dynamics basically, x dot equal to f of x ut. So we need to control x by controlling u. So u is the control parameter, x is the controlled parameter. So in our robot case, x is the position, u is basically velocities. And as per the sliding mode logic, we will define a sliding function. So s of x is function of this system parameter. So where this function s of x is positive, there is one controller u plus, and when s of x is negative, there is another controller given by u minus. So this is basically variable structure control. Depending upon the value first, there are two types of structures. So the controller structure varies. U plus and U minus. U plus and U minus are not constants. These are two different functions. It's not a constant. Okay. So this two function will toggle depending upon the value of s. So s is computed a very sampling instance. S is function of x. I will show you how to define s of x. So this, depending upon s of x, this will toggle. And again, there is another function you can see at the bottom of this slide, s dot equal to minus k into sine of s. So this is also true for designing a sliding mode controller. Okay, this is called reaching low. So as per this law, if you just look into this law, so we are designing the system based on this law, reaching low, given by s dot equal to minus k into sine of s. From this law, if you just look into that, sine of s has only three values, plus 1, minus 1, or 0. When s is greater than 0, that is s is positive, sine of s is plus 1. When s is negative, sine of s is minus 1. When s is 0, it is equal to 0. So s dot can take only three values, minus k, plus k, or 0. That's it. When s is positive, s dot is negative, it's minus k, right? When s is negative, s dot is positive, and s is equal to 0, then s dot is 0. So the observation out of this law is that this s and s dot always have opposite signs. Okay, and again, this is a differential equation with discontinuous right hand side, so it's quite difficult to solve this equation. So anyway, we're designing this control law u plus and u minus such a way that this law is satisfied. S dot is equal to minus k into sine of s is satisfied. Now we'll see how it will work. So this is a logic not only used for control technique, it has been used in many applications, sliding mode logic. So this, as per this logic, see, in this case, is suppose at a particular time instant t is equal to 0, the s of x is computed, the sliding function is defined, it will compute. And if suppose s of x is greater than 0, then what will happen? U plus is triggered. U plus is triggered. So when s u plus is triggered, s is greater than 0, what will be s dot? S dot is negative. When s is greater than 0 means s is positive, then s dot is negative. S dot is negative. S dot is negative means s starts decreasing. Okay, s is decreasing, and s decreases and keep on decreasing, and it goes to negative region. Okay, keep on decreasing. So keep on decreasing and s becomes less than 0, then immediately u minus is triggered. So when u minus is triggered and s is less than 0, you can see as per the reaching low, s dot becomes positive. S dot is positive. When s is less than 0, s dot is greater than 0. So s dot is greater than 0 means s starts increasing, and finally s becomes greater than 0. Okay, s is less than 0 means s dot is positive. That means s is increasing, so keep on increasing, and then finally it crosses the 0 region and goes to the positive side, so that s becomes greater than 0, and u plus is triggered. U plus is triggered. So control has been commuting between this u plus and u minus. Is it? So it will always, we can say that, but it will not go far away from the positive region or negative region. But if we are designing this controller u plus and u minus such a way that this low is satisfied, that way we are designing it. The design technique is like that. Okay, this condition is satisfied. That based on that only u plus and u minus has been designed. So always this, when you're, as long as you're applying this control input, this law is also satisfied. So we can always ensure that the trajectories will stay close to s is equal 0 region if you're applying this control law, because when s is greater than 0, this is triggered. Finally s dot becomes less than 0, so that your trajectories will starts decreasing, then again s becomes less than 0, u minus is triggered. Immediately then s starts increasing, then becomes s becomes greater than 0, u plus is triggered. So the control will commute between u plus and this u minus. Okay, it will not go far away from s greater than 0. S is equal to 0 in the positive side as well as in the negative side. Always stay close to that particular region in the state space. That space is equal to 0 region. It will stay there. So we can constrain the trajectory to a particular region using this logic. That's a important attraction of this. So using this switching logic, we can always constrain the trajectory space along a region. In this case, region is basically the region where s is equal to 0. Okay. So we are using this logic for designing the controllers. Okay, for, of course, in the controllers, we are using the controllers to constrain the behavior of the system, right? So we can constrain the behavior of the system in the way we want if you are applying this switching logic. Okay, using this reaching law, we design a controller based on reaching law, and we are applying this the variable structure control. We can always ensure that we can constrain the trajectory to of the system to a particular region. So anyway, so this is the general equation for sliding surface. There are many variants are there to design a sliding surface, but this is generic equation for defining a sliding surface for tracking control. X tilde represents the error. Error means we want to control the system parameter. So x is the system parameter to be controlled. xd is the desired parameter. We need to make x to follow the desired trajectory. So x minus xd is the error, basically tracking error. So this s is a function of the tracking error. So finally, when we are constraining the trajectory to a region where s is equal to 0, s becomes 0 means x tilde becomes equal to 0. X tilde is 0 means error is equal to 0. Error becomes equal to 0 means actual state minus the desired state is equal to 0. That means actual state is equal to the desired state. Is it? So in our case, robot case, actual state means the positions or velocities. So we have a desired trajectory for the position and velocity. So that's our aim. We want to make this desired actual position and the velocity to follow the desired position and the velocity. So basically design step means we have to define a switching function first. Then of course we have to apply the control law, and then we have to plug in this using the control law. We will define the controller. Okay, control law is defined such a way that this reaching law is satisfied. Okay, we'll take s, then we'll take the derivative and design it. So now then, moving to the sliding mode approach, there are many limitations are there, like actually because of the flickering of this happening in the sliding mode, because of the signum of term, then the adaptation, field requirement. There are many issues are there, real-time implementation issues, speed of convergence, many things are there, but we can do for some improvisations to improve these algorithms, sliding mode approaches, sliding mode algorithm. So one of these disadvantages, you can see this inside this u plus and u minus function, the sign of a term will comes inside this controller law. Then designing the controller, k into sign of a term as such will comes inside this law. So the sign of us means sign of us, I told you, it can take 3 values, +1 or -1 or 0. So based upon that, this value is is equal to minus k plus k or 0 because of this abrupt switching of this value of this function sine of us. So it becomes control becomes little can be there can be some flickering in the control input. So that's called chattering, and there's one of that. And again, chattering can happen due to modeling uncertainties also. Okay, so it's not because of the sine function. So we can approximate the sine function by some hyperbolic tangent function or saturation function or some smooth transition functions to approximate the sine function. So smooth transition from +1 to -1 and +1 to 0 or something like that. So anyway, the many improvisations are there to improve the sliding mode control. One approach is like using the fuzzy based approach to this one for smoothening the sliding mode performance. So the first, I told you some case studies I'm going to show. The first case study which I'm going to show is on fault-tolerant multi-robot coordination as the example. Okay, we have a multi-robotic system. So we need to coordinate multiple robots. At the same time, that we have multiple objectives. So we have multiple robots. So one of the robot is a leader, and the rest of the robots act as the followers. And at the same time, the followers has to follow the leader with a desired offset, and the followers doesn't know about the desired goal point. Follower doesn't have any idea about where it has to navigate. Only the leader knows about the goal point. But only the thing follower has to do is follower has to just follow the leader with a desired offset. But I told you about there faults can happen in the system, is it? So multiple robots are there. In that case, one of the robot is going to faulty. How will to deal with that? And again, I told you two types of fault I told you. One is like major fault, second is called the minor fault. So these two faults I have already discussed, major fault and minor fault. Major fault means a major fault happening in the actuator or sensing part so that the robot need to be isolated. Second thing is called minor faults. Minor fault means with the minor faults, we can think of fault-tolerant algorithm, so that actually the minor fault, the system can continue the mission. So this is the case where we are dealing with the first one. The first algorithm basically deals with formation control with minor fault. Formation, we have multiple robots where one of the robot is a leader, rest are followers, and one of the robot is having some minor fault. Minor fault is basically, it's not a major fault. So in that case, how the system will adapt to that. So in this case, actually what we are doing is we are using an adaptive controller. We're using to adapt to the situation. Even if actually we are not keeping constants for the controller parameters, constant values for the control parameters, but made adaptable using adaptive tuning algorithm. We derived using Lyapunov theory. So then based on this adaptive tuning algorithm, the parameters of the control adapt to the changing environment. So this algorithm is simple. We are using a artificial path planning module. We are using, okay, as we have discussed. And again, a controller is a sliding mode controller. And again, this I told you this the sliding mode controller here we are using is a fuzzy sliding mode control. Okay, so it's not a conventional controller. Sliding mode control has some chattering issues. So to approximate the sine function, okay, sine of us, the reaching low, we are using a fuzzy based reaching low, the fuzzy inference mechanism to predict the to just approximate that reaching low part. Okay. So that actually it will work better smoothly. I think some of the fuzzy parameters. The fuzzy parameters are also not kept constant because we cannot. It's quite difficult to tune the fuzzy parameters for all the operating conditions. So we are making adaptively change. We are doing adaptive tuning algorithm to update these fuzzy parameters here. And adaptation low. So instead of k into sine of us, I told you we have used an different law. We have used minus k into tan h of us minus pi into s. K and pi are constants. Tan s means hyperbolic tangent function. So this is another method. So this method we use a different type of sliding surface and different types of reaching law we have used, and we have adaptively tuned adaptive tuning algorithm to tune this k and pi. And these are the two methods we used to deal with the minor faults. Okay, using sliding mode control, multi-robot system with sliding mode control. This is basically the control block diagram for one of the robots. Okay, one of the follower. You can say ith follower. This is the control loop for the ith follower. Okay, ith follower. So you have a path planning module. Then the desired path, the desired actual position is Zi. Zl means leader position. Zj means position of the neighbor. So this all things are been recorded and sensed, and path planning module desired the path, the trajectory, and based upon this, the error has been fed the sliding surface. Then this reaching law has been computed, and the net control has been applied to the ith follower. So U is basically the UI plus equivalent, UFI plus equivalent is the actual control input to the UI is the actual control input to the ith follower. Okay. So this I'm just skipping this equation. So this is basically the control equations based on sliding mode controller. So these are the adaptive tuning algorithm for this controller gains and all. So this, for more details, I suggest you to refer this paper. So this I've shown here. So this particular paper has the details of this the algorithm. So now these are the fuzzy membership functions we used, and these are the fuzzy reaching law. This reaching law for these are some fuzzy parameters. Width of that fuzzy membership function. Fuzzy basically we are using semantic language to design logic. Okay, that's basically fuzzy. Basically, fuzzy logic is based on some if-then rules. Okay, so we will define some membership functions, and based on the operator knowledge, we are thinking of it. The design logic is based on this, operator knowledge about the system. The next is like the same thing. We improvise the same algorithm with a major fault. I told you sometimes robot can the major fault can happen in the robotic system. So that means the actuator is going faulty in real time. That case we have to isolate that member completely, right? So that is this is actually the case of a major fault. So what to do with that? So we need to isolate that particular member, and the rest of the formation has to reconfigure and continue the mission. For that, we need to detect the fault. So each agent actually will compute a fault flag. So we'll compute actually using a residual. They will compute it actually. A residual is being computed. This UI minus UM. UI means actually that computer control input. UM is the measured control input. So if it is greater than certain threshold, then we can detect it is faulty or not. Each robot can find whether I'm faulty or not, as long as the computation part is fine. So of course the element is fine, so it can detect whether I'm faulty or not. So based on that, it can set a fault flag, and this fault flag is communicated with the neighboring agents. Okay, so then actually this particular agent can be isolated, especially for actuator fault. This is particularly for actuator fault. Actuator is been faulty or a particular hardware. Communication part is working fine in this case. We are assuming that communication is working well in this case, otherwise we cannot communicate the fault flag. Okay, so this is only dealing with the actuator faults. So in the case of actuator fault, so the robot can detect whether actuator is faulty or not. It can set the fault flag and will communicate with the neighbors. And the artificial potential function, the path planning function is a function of the fault flag. Okay, and again it will reconfigure, it will isolate, and it will avoid collision with the isolated member. All these parameters are inside the potential function. I told you we have multiple objectives in path planning when you're planning the path. So all these terms, mathematical terms corresponding to all the objectives has to be in the artificial potential function. So this artificial potential function, the gradient of the artificial potential function is shown here. It has all the components. This part is basically taking care of the collision avoidance with the neighbors, and the second, there's again Fi represents the fault flag. The fault flag is equal to 1 when the robot is one of the robot is become jth robot is become faulty. If it is 0, if there is no fault. This is for obstacle avoidance, collision avoidance with the isolated member. Okay, and again this is the this one, last one. This is the isolation part. Next is the next one is basically the collision avoidance, the formation with respect to leader. Okay, this is basically the potential which takes care of the formation with respect to the leader. So if it's the collision avoidance, if it's the collision avoidance potential, if it's the collision avoidance potential, so in a proportional to fj, of course. So 1 minus fj into this one. This is basically the collision avoidance with respect to the neighbors. Collision avoidance with the neighbors, it is not faulty. Okay, this is working well. So this is basically the collision avoidance. This is taking out of the collision avoidance of the faulty one. This becomes non-faulty one, and this is the formation term to maintain a formation with respect to the leader. So the experimental setup we have used, I told you, we have used a mix of Pioneer robots and Firebird sets of robots for this experimentations. So I'll show the video of this. The major experimental setup, we have used a player stage driver for this interacting sensors and actuators. So, and again, we have created local Wi-Fi network for inter-robot communication. So we have assigned static APIs to the robots. Using the static APIs, we are identifying the robots. And we are using overhead webcam to find the initial position. When the robot is a starting position, we use the overhead webcam. It's a static cam. So, but once it's moving, or we are using odometry to find the relative positions. onboard sensors. So next is Arco markers we are finding. Of course, we are putting some markers on the top of the robots. We can see here actually the top of the robots where Arco markers are being detected. Here actually the blue sign is being shown. That means it's the image from the this one, the processed image basically. So this when the particular pattern is being identified, so we are actually putting some patterns, Arco patterns over this. So there's a overhead camera. This image captured by overhead camera. And again, using this Aruco markers and marker IDs, this it can detect this particular robot and then insert the actual separation can be identified. So I'll show this video of this implementation. So this is the first case of a two robot formation experimentation which you have done using two Pioneer robots. I hope this video is visible. Let me run it. So this is basically two robot formation with one leader and one follower. Uh, oh, 1 minute. Please wait, let me try it. It's not opening with that, so let me check with this. I upload a video in YouTube. Same thing. This is different video actually, sorry. Yeah, this is the experiment. I hope this is visible for you. Sorry for the delay. So I hope this is visible for you.
Yes, sir. Yes, sir.
Okay, so this is the this experiment which I have done in NIT Kanpur. This actually here you can see there are two pioneer robots. So making leader follower based, it's a leader follower based approach. A C based sliding mode control approach we have used, and the robots are the leader is in the for this one. This one is the leader, and this one is a follower. So a follower is not known about this goal point and the this trajectory, or the leader is knowing, and follower is just following the leader. And a position which we are actually positioning it here, and the desired position is being made up to 0.5, and we are checking with velocity maneuvering, turn maneuvering, all the things we are actually testing, and velocity and turn maneuvering together. So different maneuvers we are testing in this case. Okay, here actually the robot, so here you can see it's accelerating in between, then turn maneuvering, all these things we have tested. So turning only, then velocity as well as turn maneuvering both, and this the multiple test cases we have done like this. This only the follower is not known about this the desired trajectory. It's just following the leader, the desired offset. This is two robot formation. Now we are coming to the next is fault tolerant case. So here this is a two robot case. No, this is different. This is a three robot formation. So in this case, you can see there are two robots are pioneer robots, and one is basically a Firebird 6 robot. This is a Firebird 6 robot, Phoenix Robotics. So all the robots have onboard computers, onboard PC, and all the onboard sensors. Also, major sensors are sonars. You can see the front side, some sonars are there. Is a simple three robot formation making a triangular formation. Next is a fault case. I told you the experiment which I've taught. So one of the robot is going faulty on real time, the three robot formation, but still actually the rest of the all the agents are interacting with each other. Okay, so in this case, but even if one of the robot is make faulty, the formation is not distracted. The stability of the formation is retained. Otherwise, actually one is detached. If it is not robust, then it will be affected. The whole formation will be affected and it will collide. But here you can see that even if one is detached, the rest of this two will continue the mission, and this will continue. Okay, so this under one experimentation for the same fault detection and isolation experimentation. The first one which I shown is a minor fault. This is the case of a major fault. The robot having some major fault, like actually we are isolating one of the member which is having some fault tolerance occurring for one of the member. So we are isolating the member, and again we are continuing the same issue. So this is the leader, the other two are the followers. So making it triangular formation in this case. These are some of the test cases, some of the experimentation, the similar platforms. Here actually three similar robotic platforms. So these are like Firebird 6 robots, three Firebird 6 robots making a triangular formation moving. So these are, I told you, Aruko markers. The top, this box type thing is basically the PC. Okay, it's a PC, and it's having some onboard sensors, like we can attach camera because USB ports are available. So any of these cameras we can use it, but in this experimentation, camera is not being used. Only the ultrasonic sensors are being used. An overhead camera is used for initial position detection. We are using overhead camera. Otherwise, on runtime, we are using odometry to detect it. So now next, quickly go to the next approach. So then I'll come back to the next video. A few more experimental demonstrations I have to show. So these are the results, the experimental results which I've taken for this three robot cases, and this making this formation, like the experimental real-time results. So these are some tuning results. I told you parameters, we are not keeping any constant values for this, or we have developed some algorithm for tuning the parameters of the controller. So these are the tuning response of the parameters. You can see that it is settling to certain value. We are initialized at a 0. initially all these parameters of the controller, but settling to a certain value depending on the operating condition. This is separation distance. You can see that it's precisely coming to that 1 meter distance separation. Is it? So this is the case of this. This is the multi-rub. These are the results. So these are the results for the fault tolerant case. Fault is happening because you can see that this jump is due to the one of the robot is going faulty. So the tracking error will be high in that case. So you can see that. No, sorry, this is the case of reconfiguration. No, sorry, it's not fault tolerance, it's reconfiguration. The robot is reconfiguring. That means distance separation is changing after some time. Initially, it was some 1 meter, then it is coming to 0.5 meters. So this is like the response. I'm just skipping this. This is fault tolerant results. So I'm just skipping these portions. I'm quickly going to the next test case. I told you consensus-based formation. Next one is like event triggered control. So I told you if we want, we can control the robots in 2 ways: time triggered way and event triggered way. Time triggered way means we need sense data every sampling instance, and we will give the control commands at every sampling instance. That's a time triggered approach. This one. Left hand side, every clock instance we have the sensor inputs and control commands. But event triggered approaches, we are not getting the sensed input data, and the control commands are not being given at every sampling instance, but only at event instances we are triggering the control. Okay, this is event triggered control. So but we have to design these events. That's based on Lyapunov theory. We can design the mathematical event. So when actually this control is to be triggered, or when the sense data has to be sent, or all the things which we can predict using some mathematical, there's some techniques are available to predict it. So basically, we are using Lyapunov theory for designing this. It's a stability condition, moreover that. Okay, when the stability condition is violated, in that case, actually that data has been triggered. Okay, so then that way we are designing event triggered control. So here we are using event triggered control. Event triggered control means I told you we are not sensing the data at every sampling instance, and again control is not being triggered at every sampling instance. So we can reduce the communication complexity in this case. There is no need of communication at every instant, right? The optimality, we can improve the resource optimality if you are using this event triggered approach. Is it? Communication requirements can be reduced, communication complexity can be reduced. So using this approach, that's the advantage of this. So this is the next technique we have implemented in the multi-robotic system. So this, I'm just skipping this portion. Some these are some literature review based on this. And the Sinov phenomena is something like infinite switchings. We have to wisely we have to choose this event condition, stability condition. Sometimes actually Sinov phenomena. Sinov phenomena means lots of infinite number of switchings in finite time. That's called Sinov phenomena. So we have to derive that. We have to define this event trigger condition such a way that infinite switchings to infinite time. That's Sinov phenomena should not happen anyway. So that is this is the block schematic of this proposed approach. So here we are having multiple robots. Chief is the leader, deputy is the follower. Okay, so there can be multiple deputies. This is block diagram for one of the deputies. Okay, n the deputy. So this can be a number of deputies that are possible. So here a consensus-based path planning, because here actually all the agents are not communicating with respect to each other. I told in the case of birds. So there's a communication framework. Here in this work actually we are making a graph-based approach. So using a graph, actually the robots are communicating, and again we are using a sliding mode approach and event triggered approach. We are actually following event triggered sliding mode control. So based on there's an event condition we are deriving based on Lyapunov theory, and this event condition is checked every instant. When the event condition is satisfied, this switch is closed, and so that control will pass through this. It will be given to the deputy or the follower. Otherwise, the previous instant control input is been held by this order hold and is been given. Control input is given. So this communication link is been closed only when the triggering condition is satisfied. Event condition is satisfied. This triggering condition is derived based on Lyapunov theory. And again, sensing can also be made event triggered. In this case, actually sensing is not based event triggered, so that's called self-triggered approach. So here actually the control has been event triggered, only the control input is given only at event instances. Based on a triggering condition, we will decide whether the switch is closed or not. If this condition is satisfied, then we will close the switch, then the control is updated. Otherwise, the switch is open, so the previous instant input is given to the deputy. So this communication between this this deputy and this one has been reduced. Especially the controller is that suppose the off board. It's a remote location. If you're controlling remotely, this has more relevance actually. So when you're coming to this experimentation, so I'm just skipping this. Already I used the same this model also for the robots. This has the theoretical results. Sorry, it looks a little clumsy, but these are theoretical results. Theorems such as of this. If you want to know the more details, there's some paper being published in IEEE Transactions and Control System Technology. So this is the this paper has more details about this event triggered formation control based on sliding mode approach. All the formulations and the event triggered designs based on Lyapunov theory has been explained in this. So now these are the three basic theorems. One is like actually for stability proof based on Lyapunov theory. Second theorem will talks about the convergence, consensus, convergence, formation maintenance to prove that. The third one is to avoid phenomena. The inter-event sampling, inter-event time has to be bounded. So that has to be geometric. So these are three proofs actually. So I'm just giving that. Now coming to communication topology. So here I told you this is a multi-robotic system having one leader and multiple followers. I told you all the robots are not communicating within each other. That's a graph. So this is a graph which I've used for one of that. So initially for simulation, then we have done for the real-time experimentations. So for the simulation part, we have used actually 4 robots. We have used a player stage simulator. So in this case, 0 represents the leader and 1, 2, 3 represents the followers. And here you can see that all the agents are not receiving the data. You can see that. The agent number 3, if you just take the robot number 3, is getting information from the leader, but it is not receiving any information from the other agents, right? Because information is passing from 0 to 3. Is it not from any other agent? So 3 is getting all information about the leader only, but 2 is getting information from the leader to 1 and 3, all the members. But 1 is what about 1 is getting information about 0 and 3, and but it is giving information to 2. Is it? So means all the members are not being connected. So we have a communication topology. So there can be different types of communication topologies. Switching topologies are possible. So you can switch according to the operating condition. So we can think of that. So this is a particular fixed topology. In this case, we have used a fixed topology. So based on the framework, these robots are communicating with each other, but it is maintaining a formation. So this is the I will show the video of this. So then. This actually, the first one is a simulation experiment. Second is a real-time experiment. So simulation, I told you, I've used a player stage simulator. There are many simulators are available for multi-robotic system or single robot experimentation. If you want to do, player stage is one of the simulator or mobile sync. Player stage and mobile sync are the 2 open source softwares. You can use it for simulations, and it will work perfectly. And if you are implementing real time, the same code will work. So that's the advantage of this type of simulators, okay? Because they have the realistic models. So this for the robots, for all the standard robots like Pioneer or Turtle bots and all the standard type of robots, research platforms, they have their own models. So we can think of all the algorithms which are derived based on the kinematic unicycle model we designed using the approaches we discussed, and we implemented in this, and we are real-time implementation also the same thing will work. So there is not much tuning required when you're implementing real-time after implementing simulation. So this is, let's see the simulation first, then we'll go to the real-time implementation. So here you can see that these are the 3 robots, this one. So this is a player stage simulator. Here the red one shows the leader, and second all other 3 are the followers. Because this initially you can see these are randomly placed. They're randomly placing this formation agents, but they are supposed to make a square formation. See, it is making a square formation. It is coming back. The square formation is following that. And again, it is not that only the leader is knowing the path, and all the agents doesn't know that. It is just following this leader, but leader is not on the front side. It is on the corner, on the back side. But you can see now how it will work when we are perturbing one by one. So you can see that. And again, one more thing I told you, this all the agents are not interacting between each other based on the graph. The graph I have shown, based on this graph, these agents are communicating. So all the agents are not connected with each other, but only few, but still they are making square formation. Let's see, and leader is perturbed. We are disturbing the leader. Now we can see that again it's coming back to the formation. Now I'm disturbing one by one. Let's see how it will work. So here I'm just going to perturb the next one. This deputy number 3, there is a follower number 3. See, the 2 agents are affected. Leader is not affected because leader is not getting any feedback from other members. Leader will continue the formation. So now it is again coming back to the formation. It is making the square shape formation. It's coming back to that. Now we'll disturb the next agent. See how it's affected. Deputy number 1 is being disturbed. See, only one of the agent is being affected. See, this blue is not affected. Why? Because it is not connected. I told you it's a graph, but still see it maintaining it. It is not colliding. It's making this square formation. Now it's disturbed. See, green is disturbed, and we can see that none of the agents are being affected. See, look back here. You can see this graph. It's clear because it is not. It is this green one is receiving this data from the other agents, but is not sending data to the other agents. That's why even if it is disturbed, other agents are not affected. But it is coming back to the formation and so retaining that formation. So, but later it's put up, of course, all the agents are affected. Then actually this it will be reconfigured. So not reconfigured. It can comes back to the formation within very short span of time. It's very fast enough. Now this is the simulation which I've done using Parastage. Next is the real-time experimentation, which I've done using 3 robots, leader and follower. So these are like these 3 robots. Here this leader is a Pioneer robot. Sorry, a Firebird 6 robot. The followers are Pioneer robots. So here it is at 3 or 4 meters apart. It's supposed to come to 0.5 meter separation. Desired distance separation is supposed to be 0.5, but actually it is kept at some 4 or 5 meters apart. But it's coming back to 0.5 meters and it's following the leader. Okay, so this is basically event triggered approach basically. So it's not little slow here. You can see that you can you're checking the different maneuvering, velocity maneuvering, and turn maneuvering. Then velocity turn. All the 4 test cases we have done. Velocity and turn maneuvering together. All the 4 things. The 3 robots. So the leader is aware of this. So little sluggishness because the second one, same thing actually. Same thing. The robots are far apart, 4 or 5 meters, so it's supposed to make some 0.5 meter separation, distance separation, and follow the leader. Leader is here, and these are the followers. So here actually we are not giving control commands at every sampling instance. It's an event triggered approach. Okay. Only at event instance we are actually commanding that. So it's just following the leader of the desired offset. Same experiment repeated and stopping somewhere. So this is these are other. Then there are many other experimentations we have done here. So now I want to show another experiment. Yeah. Yes.
Yeah.
Hello. Next is.
Sir, please continue. Please continue, sir.
Okay, sir. Thank you. Yes.
We will take 5 minutes question answer session after you finish your lecture.
I will take 2 or 3 minutes more. That's it.
Okay, sir. Thank you.
So this the next is the experiment which is done at IIT Kanpur with Meenakshi Gupta. She is my lab mate here. She's working human tracking. So she's human tracking is also like a multi-robotic system. The robot is supposed to follow a human being. Okay, so it's a multi-agent system basically. So, but one of the agent is it's a human being, but follower is basically a robot. So basically, it is having a camera on board, and the robot will detect the human being and just follow it. Lots of applications in assistive robotics, like for wheelchair and all. So wheelchair has to follow a human being to track it. You can do the application. It's a multi-robotic system basically. It's a multi-agent system. So here you can see that robot having onboard cameras detecting a human being. When this human being comes in the field of vision of the camera, see robot is coming close towards the human being. Once it detects it, it will stop and making the desired distance separation is following that human being. So here's a human being. This is actually onboard camera he's having. A Firebird camera is having. So then it's detecting the human beings following that, and when the human is going out of field of vision of this camera, the robot will stop. That's the first experiment. Second experiment, that improvisation has been done to for predicting that predicting the human being. Okay, using some UKF algorithm to predict the human being. Even if the human being is going out of field of view of the camera. So, but in this case, you can see if it is going out of field of a human is going out of field of view, the robot will automatically stop. Okay, but the next improvisation is like this is actually when again it coming back to the field of view, it will continue to follow the robot for the agent. This is one of that. So second is like again many human tracking algorithms are being implemented. This is also work done in the Intelligence Systems and Control Lab at IIT Kanpur. So this This is from the camera view. This is a human being. Onboard camera is detecting it. So this from the camera. This is from the camera view. So now the external is using external camera also. We can show how it works. It's a robot actually. Onboard camera. It's been recording this. Okay, it's detecting the human. Even if occlusions are happening, so you can see that when it's detecting the human, it's following the human. The robot is navigating, but even occlusions are happening because some crossings and the out of field of out of plane rotation, all the things it is able to deal. So this is done by Meenakshi Gupta. She is working in the area of human tracking. So here you can see that this is one of this is from the external camera. So here you see the occlusions are happening. Still, the robot is following that the human. So it's an onboard. You can see that the laptop is also placed on it. We are bypassing the onboard PC here. So because the onboard PC doesn't have much computation capability, especially image processing. So we are using an external laptop to do the onboard processing. So it's following the human being, but even occlusions are happening. So even crossings or all the things, all the disturbances are happening. Still, the robot is detecting the human, and again, it is following that particular human only. Based on template map, there are many algorithms of this human tracking. So this is also multi-agent system. This is, I told you, you can use it for assistive robotics. So you can think of a wheelchair. So a chair is attached to this robot becomes a wheelchair, right? Wheelchair is a mobile robot. It's a chair with a wheel attached to that. So in that case, actually, assistive robotics. So it can follow a human. The chair can follow a human. We can think of extending this one. This is one of the applications. So there are many other. So there's one more video. I just want to. This is like the routing based approach. So it's okay. I'm just leaving that part. So now this is another approach. This is basically routing based. I told you we are using cyber physical robotics is another one. Okay, where actually we will consider the path planning based on cyber parameters also, communication parameters. So this is basically a sliding mode approach only, but we are taking some communication parameters also for applying the path. So artificial potential function becomes a function of the communication parameters like link reliability, the probability at which the data sent from one node is decoded at the other end successfully, all these things. So these are some of the works we have done. So, and these are the results actually for this event triggered approach, which are experimental results. So which I have already shown, and the details, if you want to know, you can refer all the test cases just shown. The three works which I was trying to show. So one is the fault tolerance, second is event triggered, third is routing optimal mobility and routing control in multi-robotic systems, the cyber physical framework. So these are the three test cases, case studies I've shown. So this papers will give you the more details about this works. And thank you so much. So that's all about this. And if you have any questions, please feel free to ask. Hello. Hello. The voice.
Yes. I would request all the hands.
Yes.
Someone is raising his hand, so you can ask your question, please. Please unmute yourself.
Yes. Yes, Ms. Lekrat, Mr. Lekraj Patidar, please ask. Hello.
Yes.
Please, but somebody has raised that hand, so please ask. I'm not able to hear anything.
Okay, sir. Thank you. If you are having any queries, you can send it through email, and you can talk to Dr. Ranjit.
Yes, of course. You can email. Yes. The email ID is available on the Pune website. You can contact.